As I thought. Sketchy. I've never done this before. Oh, here's Sammy's.
She's got it.
I got 3. And I got 5. That means I got 6 wrong. I still didn't get 6. And I think I got the bonus wrong too. How did I get it right? And then where did I go wrong? Because I only got 1 wrong. I got 6. No, I mean I only got 1 thing wrong. I took off 2.5 points. It's just one. Yeah, it's just one right now. So they all work 1.5 points, or did I get something sort of wrong? Let's see if I can get it for 6. Oh, there it is. I found it. Oh yeah, 6 wrong. That's part of the problem. What? Is the price per shirt? Oh yeah, I forgot to put that.
I have a food.
Did I? Did you get 6?
I think that I have food. Oh, the night. Yeah, they did.
Kurt?
I did not.
Hey, Dale.
I love the hedgehog one.
Yes.
Sammy doesn't have a voice today. Just FYI.
Oh, okay. I'm sorry you don't have a voice today.
She's in whisper mode, just in case you call on her.
But who's going to speak for her? You going to speak for her?
Brittany's gonna speak for her.
Since Brittany's not here to defend herself, she got voluntold.
Exactly. That should make perfect sense if I have a whiteboard. What did you put on the lap for 1 and 2? That's what I tried to say. I'm just not as good at writing it down.
Pardon me? Okay.
So yeah, so the minimum amount of fencing would be it was like 800.
Or maybe it's 0.1, I can't remember.
How big is their campus if they have a lake in it?
It's very mountainy.
Cool.
It's hilly.
Cool. Brittany, I realized something. It doesn't matter how early I sleep. I'm never gonna get used to waking up.
Oh,
This early. I slept at like 9:30 yesterday.
I need that too, but because pretty much I feel showing how much there is. It's like the best thing ever. I love it so much, but I don't know what it's supposed to be. But like, is that what zero like? No credit.
I think it's 600.
Because they're gonna do everything. That's kind of three. Yeah.
What do you do Brentwood or something?
I did. I didn't even really look at our names. Actually, kind of clear some really not even sure who the characters are. It's fine.
This is Black Eyed Orinoco. It's basically perfect.
Yeah, I know.
And then
That's
there's
what I
two
know. And he
Orinoco.
was a slave owner, but then he turned into a
No.
That is life's.
Yeah.
And then,
And then he for honor.
He got 20 dollars.
Cool. Does anyone else have a story?
I mean, there's like the me and white.
Trigger school.
It's really weird, yeah. But some people got the first novel, which is pretty interesting. It's a relatively new style, actually. However, I attribute it to some East Asian literature. That Orinoco. You sound
You didn't get
satisfied.
6, did you? Oh, you got. Oh. On the test
Wait,
Oh,
numbers.
yeah.
I thought you meant something bad. Numbers take it on. I thought I did that. And then, is the bonus all? Is that it? That's for sure.
How to get started. So you have your test corrections back. Lab set. Any questions on that?
Yeah. Can you just walk through number 6?
Walk through number 6.
The trough.
Here's number 6. I walk through it.
How?
Oh, what is number 6? I don't even have a copy of the test.
That's the one.
Oh, we did one like identical back in class.
Yeah, we did, and I analyzed it over and over.
No big deal.
Oh.
What were the specifications on that?
Water. Yeah.
I guess the key is probably has to do with that it's got an equilateral triangle.
Mm-hmm.
These are 60 on the side, and this was 400 or something like that. And you're supposed to find dBdt. Then what? H is 8. You're given dHdt is
At 8 centimeters is -3.
okay. So I just have to find out the volume of that thing. So volume equals area of the base times overall length. Area of the base 1/2 of little base times little height. It's a triangle. All I gotta do is figure out what B is in terms of H, and I'm 99% done. Okay, so area of a triangle will have this type. I want little h involved because that's the depth of the water. So we get this water in here. So there's h. So all I have to do is figure out h in terms of b. B must be this distance right there. By similar triangles, let's see. You have 60, 60, 60, B, and I got H. I'm guessing this distance here is somehow related to the fact that it's equilateral triangle. I don't know. So I guess this would be, think of it as half of a right triangle like that. This is 30, 60. Just big height here. calculate that.
It's 30 root 3.
Yes.
What is it?
It's 30 root 3.
30 root 3. Okay. Is height. So now I've got, I'll find little b to little h, so that's 60 to 30 root 3. So b must be 2 over root 3 h. 1/2 times 2 over root 3 h times h times 1. From there, it's differentiate, plug and chug.
Is that what you did? Is that...
I think.
What did you get? What was your answer?
But here's my question.
Okay.
Why is it dH over dt that's given? I thought it was the other way around.
No. I got a DH over DT.
I thought what
did.
you're given and what you're looking for are flipped.
That's exactly.
Sorry, what now?
I thought that height and volume were flipped in your given and what you're finding.
I don't think so. I'd have to read the problem up there with it and see a copy of the text.
A dt when h equals 8, that's not a definite value.
Okay, the directions say 400 centimeter long water trough shown below has ends that are equilateral triangles whose sides are 6 centimeters to the nearest 100. Some of us don't know what 100 is, by the way. Find the rate at which water is draining out. Right there. Find the rate at which water is draining out.
Yeah.
Water is measured how? By volume.
Yeah.
We're finding dB/dt if the depth of the water is dropping. So if that means that's my hypothesis, if the depth is dropping at 3 centimeters per second. So I'm giving you dH dt is -3, and we're trying to find dB/dt.
Okay.
Can I see you?
The if gives me the hypothesis there. And so I stated it so that the to find is the conclusion, if you will, came first with the if after. Okay, that's standard English practice. Okay. So, obviously, if you look at your rework, you'll see a check minus on a couple problems. What I did there was, the rules are on extra credit. You have to do all the problems. You have to do them 100% correct to get credit. But on a couple papers, for example, it asks for two things, like it asks for the price per shirt, the bonus problem, and the total maximum revenue. So two things. If you did the work correctly and only gave me one of those answers, meaning it gave me the total revenue, instead of marking the whole thing wrong, I gave you a check minus, and I counted as half of the check. There's 2 or 3 or 4 people who only gave me one of 2 answers when it was required for 2 answers. Since you got the one right, that meant you knew what you were doing. You just forgot to finish the problem, so I gave you half the check on that. Okay? So if you found the check minus, that's probably what it was about. Okay. Well, today we need to start something new, I guess. Good chance, by the way, to practice with the sigma notation. Get a little better about that now. I'll be using that coming up. That's going to be part and parcel of what we're going to be doing in the near future. And so that's why we practiced with it for a couple of days to get comfortable with that whole notation and how to work with it and how to do limits with it. Today we're going to introduce something as just another foundational vehicle to get us going, called a Riemann sum. Riemann was a mathematician back a couple hundred years ago. By the way, there is something called the Riemann hypothesis that we're not going to get to. It's way beyond our scope in this class, way beyond our scope. It has been, it's a theorem that Riemann put out there 150, over 150 years ago, and no one's been able to prove it. Everyone believes it's true. There's been a lot of attempts to try to disprove it by collecting lots of data. And the only way to disprove is to get all data. And you can't get all data, so that's not really a good method. But to directly prove it mathematically, no one's been able to do. And so there's some big money on the table if anybody can come up with a proof of Riemann's hypothesis. Of course, great minds are working on this for 150 years, and no one's been able to prove it yet. But I'm encouraging you to take about a couple of us have jokingly referred. That's what we're going to do when we retire. We're going to sit down. We're going to prove Riemann's hypothesis. Anyways, so we're going to define something called a Riemann sum. So to define that, I'm going to start by we've got a function. A function f of x on interval. Say it's hard to draw a picture on the interval. Could be. Create n subintervals of length delta x equals to b minus a over n. And choose any value x sub k star, we'll call it, in the k subinterval. Riemann sum is summation k equals 1 to n of f of x sub k star times delta x. That's just a definition. What is it all saying to me? Okay, graphically. So, got a function f of x. So I'm going to draw a picture of a function f of x. I apologize. I'm going to cover that part of my definition there for a moment. Here's some function f of x on interval a to b. This is kind of where we started on all of this some time ago. There's a, there's b. And then it says create n subintervals of length delta x equals b minus a over n. So the idea is, like we showed before, I'm going to subdivide a to b into subintervals. I'm not going to do all of them. I'm going to leave it generic. So I'm not going to do an exact n. I'm just going to leave it as n. Okay, so I have now n subintervals. So n subintervals. the distance of each little subinterval has a length of, we're going to call it delta x equals b minus a over n. Let's make sure that b minus a over n makes sense to us. Look at this formula, b minus a over n. What does b minus a calculate when it puts b minus a right there? What are you calculating when you do b minus a?
The whole interval.
Think of the interval from a to b. That's b minus a. And if you divide that by n, that's going to give you the length of each of the little subintervals. So this distance in here is delta x, which is equal to b minus a over n. That's true for each one of these little subintervals. All delta x.
Yeah.
Delta x, like we saw when we did derivatives, delta x is a small change in x. Okay? Derivatives, we're talking about small change in x versus small change in y for slope. It's a small change of x, but how is it being used? Small change of x is a width of a rectangle, is what it is now. Okay, other things that we've talked about before is numbering these terms, these x values. So we started off with x0 is at a, x1 is 1 delta x step over, x2 is 2 delta steps over from the original, x3 is 3 delta steps over from the original. The last term will be called x sub n. So the previous term is x sub n minus 1. The term previous to that is x sub n minus 2. So I've got a bunch of x values lined up there, all of them equally spaced by a distance of delta x. Okay, so then it says you have to select any x sub k in the kth subinterval. So let's make sure we're clear what we mean by the kth subinterval. Change colors here. So what in the world do I mean by kth subinterval? So the interval, first interval is the interval from x0. Let me write this a little bigger. I'm getting small here. So the interval from x0 to x1, that's my first interval. The interval from x1 to x2, that's my second interval, and so on. So in general, we can say that the kth subinterval how would you write the kth subinterval if I had to use similar type notation? The first subinterval goes from x0 to x1. That's the first interval there. The second interval is from x1 to x2. So what would the kth subinterval be? Yes. X sub k minus 1 to x sub k. Notice, like, again, on the second subinterval, the right-hand endpoint of the interval is x2, and the left-hand endpoint of the second interval is one less than that. So same thing here. The kth interval will end at, right-hand end will be at x sub k, wherever x sub k is, and the left-hand endpoint will be one left of it. Okay, so what we want is we want x star k. So this is in the kth subinterval, there's a special value called x star. So you go to any interval here, and you're going to locate a special value called x star, and that's going to form your height of your rectangle. So we would say that instead of writing equals, I'm going to change this and put element of. So x sub k star has to be, what I'm saying right here, all this green, I just wanted to get you to see, that this special x sub k star has to be a member of the K subinterval. So any x value in that interval can function as the location where I calculate the height of my rectangle. Now, when we first introduced this, we were just doing certain things, but it could be anything. The x sub k star could be the left endpoint of the interval, like here, or it could be the right endpoint of the interval. It could be the midpoint of the interval. It could be anywhere. It could be 1/10 of the way if you want it. Riemann doesn't require it to be a specific location. It just has to be in that interval, any value in there. So what is this calculating? What is this Riemann? This is called Riemann sum. What does it calculate?
Oh.
Area of the n rectangles.
Mm-hmm.
The area of the n rectangles that is approximating the area under the curve between the x-axis and the curve. Okay? Those rectangles may not be, they may not be a lower bound or an upper bound, but they could be. We could define what we mean by a lower bound and an upper bound. In fact, let's go ahead and do that. So this is a general class of things called Riemann sums. But we can do some special cases that are meaningful to us. So some special cases. Do they use lower bound sum, or they just call it lower sum? They just call it lower sum. Upper and lower sums. Okay, so a lower sum. Lower sum is a Riemann sum. Where x sub k star is located so that f of x sub k star is less than or equal to f of x for all x element of minus 1 to x sub k.
Oh.
Make sure we're clear what that's saying. I want a lower sum. What do we mean by lower sum? That's like with the lake, we have a lower bound.
Yeah.
A lower sum is simply a sum, an area, that's always going to be too small.
Wow.
Like the lower bound in the lake, you completely closed your figure inside the lake, and that was always going to be too small because it never covered all of the lake area. Well, same thing with a lower sum using Riemann sum. We're going to specially pick our x sub k star. Each interval, you get to pick one point in the interval to represent that whole interval. So for a lower sum, you're always going to pick it so that there's nothing else smaller. The height at this special point is always smaller than or equal to every other height in this interval, is what that says. So for this first interval, which endpoint would you pick? Make sure you're getting a lower sum. You would pick the left one to get the lowest sum. On this one, you would pick the left one to get the lowest sum. On this interval, you'd still pick the left one. On this interval, you'd probably pick the right sum. It depends. If an interval were to change directions within the interval, you might have to pick some other point. But you're always going to pick the location so that the height is the smallest possible within that interval. Okay? Well, how do you change it to make it an upper sum? This is going to be ditto, 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 except, we'll keep going, ditto, second line. The third line is going to say f of x star sub k is what? Greater than or equal to f of x for all x in the interval. So the only change to go from a lower to upper sum is to make sure when you pick your special x in the interval, x sub k star we call it, that special x, make sure you pick it so that the height of the rectangle is the biggest height in that interval. And if you do that, then you'll always have a sum that's a little too big. It's always going to be called an upper sum. So those are two special cases of a Riemann sum. You're allowed to pick your x sub k star wherever you want. If you pick it so that it satisfies these criteria, then you'll either get a lower or upper sum. Okay, a couple more special cases, then we'll do some examples. The special case, lower, upper sum, then we can have a left sum. If the book uses this notation, some books do. Let me see real quick. I'm just going to go ahead and throw it up there and see. Hopefully it'll be off with it. So we're gonna call it L sub n. If I could make it a function, call it L of n. How about that? We'll make up a new notation. L of n. So left sum of n rectangles. Left sum of n rectangles. How might you define that? Again, we're just going back to that same graph that we referenced before. And I always want to, now instead of lower sum or upper sum, I always want to do the left sum. So what do you think that means? It's always going to be the left end of the interval. So how do I state that?
The leftmost point of each subinterval determines the heights.
Yes, good. So the leftmost point. So let's how do I use that with this kind of notation? This is a Riemann sum. Where x sub k star. So Riemann sum has this special x you get to pick. This time you're always going to pick it as the leftmost endpoint. So what's it going to be? Let's scan back over here to this picture. Okay. In the first subinterval, I want to pick the left endpoint, which is x0. In the second subinterval, I want to pick the left endpoint, which is x1. In the third, in the k subinterval, I want to pick the left endpoint, which is x sub k minus 1. So x sub k star has to always equal to x sub k minus 1. Let's spend a little more time on this one now for a moment. So what's that going to mean in terms of that? So if we do that, we're going to have, so the Riemann sum now becomes, so we get Riemann sum
K equals 1 to n.
of f of what? Instead of
X
the standard
K.
or the generic Riemann sum, we're going to replace x sub k star with
X sub k minus 1.
k minus 1.
Got him.
That was easy.
Yeah.
Let's write out what that means to us, folks. Again, there's some more to this that we need to dig into. And I'm going to show you a couple ways of viewing this. One of the methods I'm going to show you is good if you're only doing n as a small number, like n is 10, and you're going to manually compute the area. But what if I wanted to do a better approximation, like on the lake, and I wanted 1,000 for my n? You're not going to want to do it by the same method. Hint, you're going to want to use the sigma form and build a formula that you can calculate like you did on last night's homework. So I want to evaluate this in a little more detail. So one way of rewriting this is literally let k be 1. So if k is 1, what are you calculating here? If k is 1, then you've got f of x sub 0. So this is f of x sub 0 times delta x plus, then when k is 2, f of x sub 1 times delta x, and when k is 3, f of x sub 2 times delta x, plus dot, 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 plus, and then what's the last one? When I get to n, my last term is going to be what? F of what?
N
F
minus
of
1.
x sub n minus 1. That's right. F of x sub n minus 1 times delta x. Notice we did not use x sub n in that expansion. Why did we not ever use x? We did not use x sub n in the expansion. Why not?
Because we on the right.
Right in. We want left hand. Now, I'm going to, again, show a pattern with some other things we're going to cover. I'm going to factor out a delta x here, just so you can see that. So I could write this as f of x sub 0 plus f of x sub 1 plus f of x sub 2 plus dot, 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 plus f of x sub n minus 1, all times delta x, like that. That's a convenient way to work with it, especially if you have a small number of n. If n is relatively small and you need to manually calculate, even with a calculator. When I say manual, I mean with a calculator, not necessarily all in your head, but not using a computer or some other technology that can really get the job done for you. So that is a convenient way to do a left sum right there for a small n. But there's one other thing I want you to see, because if the n is very large, so far what we've got is kind of cumbersome, and there's a better way to view it.
You're right.
That's going to take a little bit of discussion, so I'm going to go back over to the board. I want to remind you that x0 represents A. And I want to also emphasize that, so this is equal to A. That number there is referencing A. That number is equal to A plus delta x. Y'all see this? And that number there, referencing A, is equal to A plus 2 delta x. See this? And so on. A plus 3 delta x. Dot, dot, dot. A plus n delta x. Does that make sense to everyone?
Mm-hmm.
That's important because I can now build a formula that I can easily use my sigma work that I've done before. So I'm going to go back over here and see if I can build that here. I'm going to rewrite a sigma form for this, but instead of using x sub k minus 1, I'm going to use what I just discovered over there. So I'm going to rewrite it in a sigma form that's now useful for very large n. I want a little more space than that. Okay, so what what am I going to write here? I want to generate, the whole idea once again is, I want to generate x0, x1, x2, and so on. Those are the x's I want to generate. But instead of using x0, x1, x2, I want to use A as a starting point and get to each of those x's by adding on delta x's, just like I went through right here. So how can I get these?
Is it gonna be like a plus k times b minus a over n?
Pretty close. What did it say that again, Rizzo? A plus what?
K.
No, I think it's N.
Almost. Think about that. If I let k be 1, if k is 1, my starting, then a plus, Rizzo's suggestion is a plus k times delta x. It's an excellent suggestion. It's almost right.
Is it minus?
So if I let k be 1, then I've got a plus 1 delta x for my first term. But my first term needs to start on left end at x0. I want to start at x0. x0 is the same thing as a. So I don't want to add 1 of my delta x's on the first step. So how can I make that happen?
K minus 1.
Or someone say it.
K minus 1?
Yeah. A plus k minus 1 times delta x.
Yeah. Yeah.
Follow that? So think about it. When k is 1, start with k is 1. See, make sure it works out. When k is 1, k minus 1 is 0. 0 times delta x is 0. So a plus 0 is still at position A. But a is the same thing as x of 0. When k is 2, you're going to do k minus 1 is 2 minus 1. 1 times delta x is delta x. A plus delta x gets you to x1. That's your second left-hand endpoint. So, again, the whole idea is to hit, I want to hit x0 when k equals 1. I want to hit x1 when k equals 2. This has to be k equals 3, and so on when k equals n. I want to hit those x values, but I want to build it as reference to a plus this delta x. This delta x is key to all my work. So this form here is useful, and we'll do some examples, for when you have a large number of n, like 1,000 or something. And this form with the parentheses and the delta x factored out, that's useful if you have a small n, like 5 or something, 10. Okay. Any questions of y'all follow that? Let's try one more now. Now we've gone through the left sum. What about the right sum? Okay, well, let's see if you can get that figured out. I hope you figured it out now. So the right sum,
Or would it just be k?
we'll call it R of n.
Okay. What if I have
Is a Riemann sum,
well,
but it's fitting this whole category of all these things we're talking about. And it's just giving another tool of how to calculate area. Where, now here, help me out, what is x sub k star? If I'm doing a right sum, my special x sub k star that Riemann allows me to pick anything I want in the interval, which point in the interval do you want to pick to make it a right sum?
K.
Yes, x sub k, that's right. So this is just going to be x sub k. So we get same type of game. I can rewrite my general Riemann sum with that substitution in place. So I'm not using the generic x sub k star, which allows any special point. Now I'm only picking the right endpoint on all of them. And then go through this same game and see if you can. Ultimately, I want to get to this game down here and make sure we can see that one more time. So if I expand this out, when k is 1, I'm doing f of x sub 1 of x plus f of, and then when k is 2, I'm doing x sub 2 times delta x, and so on. The last one will be, what's the last x I'll use in my process? X what? Put in, right? X in. Notice this time, folks, I did not use x sub 0 in my process. Why did I not use x sub 0 in this process?
It's because you're right.
Just using the right.
Because we're doing the right side instead of the left side. So we're going to ignore x sub 0 this time. Once again, I could make a simple look for a small number of n, and that is just fact delta x. Add everything up inside. So that's a useful form and again, I wouldn't necessarily memorize that. I would just have an inkling of what the form looks like, and I can build it thinking about a right endpoint. I can build that fairly easily. I don't have to necessarily memorize all that. In fact, I didn't have that memorized just now. I just started building it from what we discussed, literally. Now let's take it one step further and build by thinking about it rather than memorizing. I want to build a formula in sigma form so that in case I needed to do this for a large number of n, I could have something I could use all of the knowledge I've gained about sigma forms. I could use that knowledge. So I want to build a formula that's useful to me in that way, in the same fashion we did over here. So what's it going to be?
What's it going to be?
F
I'll
A
tell you it's
plus
F.
K times delta x.
Got him.
F of A plus what did you say?
Plus K.
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 K. Q-U-E. K.
Times delta x. And then times delta x again. So notice, again, make sure you're reading the notation carefully there, folks. There's delta x used twice. One of them is inside the function. So it is calculating an x value for you to input into the function to get the height. So all of that is height. It uses delta x to determine the location to calculate height. And then that's just simply the width of the rectangle. So in both of these cases, you would, keep that always in mind also. This is simply height. That is simply width. That's the case on all of this that we're doing today. Keep that in mind.
Mr. Gaddis,
Test phrasing.
is there a name for the two different sums right there?
Oh, left is on the right side.
No, if we're talking about, yeah.
This and this?
Yeah.
No, they're all the same. It's all just called a right sum. To me, this is the kind of the generic starting point of a right sum. But again, if I'm going to try to build something I can compute with technology, I'm not going to go there. I'm going to start here and build to this one somehow, based on understanding how I get to those different x values with this process right here. No, there's not a separate name for it. To answer your question, short answer, no. It's all just part of the right sum. There's different looks of the right sum. I mean, all of this is equal. It's just different ways of viewing it.
All right.
Answer your question?
Yeah.
I know maybe disappointing. It's a good question. Are there different names for that? Well, if we want to, we can name them. Right sum generic, right sum useful.
Right sum useful.
So are we going to use that one more then? Is that what you're saying?
I mean, yes, I think this one's probably the one you'll use more. Because it's more useful. This one, I mean, you're going to start there. The whole point is this is the starting point. And then you can build what you need from that. If you're going to do it for a small n, then I'm only going to go so far. If I'm going to do it for a large n, that's supposed to be n, by the way. If I'm going to do it for a large n, then I'm going to do something more.
Okay. I see a test
Okay.
question here.
Let's do a couple more of these special cases, then we'll go back and because I feel like we're on a roll now. Let's do a couple more, and then we'll do some examples. Okay. Let's knock out the midpoint sum.
Like that. Oh, dude, is that like in the middle of the left and the right?
Wow, Rizzo.
Shit, dude. I'm wilding. I think I'm a little smarter than I was this morning.
Okay, so I'm doing a new, I'm going to erase my left sum here so I have to make sure I don't get confused. I'm doing the midpoint sum now. So the title should tell you what you need to know. Let's think our way through it. Again, it doesn't hurt to later sit down and try to memorize all this, but I would personally make sure I really understood it so I can build it. Because if you just try to go on memory on a test, there's a good chance you're a little stressed out and you get something confused. If you can build it, then he'll come. Come on, it's almost Monday morning. You got to go with that. Some people don't get that right. Anybody got the reference?
No.
Field of Dreams, classic movie. Oh man, you got Field of Dreams. You got to watch it if you've never seen it.
Well, how classic are we talking here?
Early, like late 80s, I think, 87, something like that. So pretty classic.
Well, I wasn't really even conceived back then, but.
You weren't really a twinkle in Dad's eye yet. Okay,
Thanks, Rizzo.
I was not.
so midpoint. What is? I'm building a Riemann sum, but I'm going to use the midpoint. So back over on my graph picture here, I'm using not the left end, not the right end, but the special point I want to pick this time is right in the middle of these two.
Crap, y'all.
How am I going to state that up here? X sub k star is a special point. It's right in the middle of the interval each time. How do I state that?
Oh, you use the midpoint formula, some
Yes.
variation of it.
Thanks, Rizzo.
Exactly. Midpoint formula. We learned that in pre-calculus. What does the midpoint formula say?
Dad,
X1 plus X2 over
I
2.
know.
Yeah. So let's do it in terms of this now.
This one is
Okay.
x sub
X
k
minus
minus
1
1
plus
plus
x
x
sub
sub
k
k over
2.
2.
Here we go. Good job. Yes, we got it. Midpoint formula. You're right. We've done that. Excellent, excellent. We've got this. That's going to give me the middle of each subinterval. You're absolutely right. And so we get, when we substitute that in, we'll go through the same type of game and see if we can build this out into the different looks of it. The general Riemann sum now simplifies down to this look. F of x sub k minus 1 plus x sub k over 2 times delta x.
Nice.
So that's the most generic look of a midpoint sum. It ought to tell you everything you need to know, meaning this is the middle of each subinterval, and I calculate the height of it and then multiply by the width. Fairly simple. Let's go ahead and break it out a little bit. What does that mean? Let's see. All of that. Oh gosh. Oh, okay. So f of, let's see, what's that? X0 plus x1 over 2 delta x plus, I'm not going to write this whole bunch of time. I'll get tired of that in a hurry. X1 plus x2 over 2 times delta x plus dot 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 plus f of x sub n minus 1 plus x sub n over 2 times delta x. This time, quick comment, quick question. Notice this time I used both x sub 0 and x sub n.
Oh, wow. That
In
makes
right
sense.
sum, I only used one. Why did I use both of them this time?
The middle.
Get the midpoint, so I gotta look at both of them. That's right. Let's see. What did I do next? All I did was factor out delta x, whatever.
It's so funny. Oh my gosh, are we factoring out the delta?
Wow, looks like we've done this.
Crap, no.
Okay, now final gambit here.
gambit. Oh, snap. Can we call it the final gambit form?
No.
For me,
Is that last
Just
one the final
ignore
gambit?
we'll
The
call
last
this the
song?
final gambit.
Yes.
So we got the initial gambit and the final gambit. So now we have names for these.
We call them X-Men gambit. Your F of X, your second midpoint, you still got your delta X.
Oh, thank you. Yeah, then I got delta X squared on that one. That's no good. This is a programmer sitting here. You're not going to run any kind of that kind of stuff by her, because
That's what I do for a living.
if you're a program, you write in a delta X in the wrong spot, you're going to mess everything up. So yes, it's got to be precise. Thank you. So now let's see if we can write this one in the final gambit version like we've done before. Let's see if we can figure that out. So once again, I want to relate it somehow to starting at A.
Hey.
So that I build some kind of formula for it in a computer program, or if I want to use my sigma notation formulas that I've learned previously for a large number of n, I'm going to start at A and get all of these terms. So we'll go back over here to the board, to the graph of it. We're at the board already, but at a different board. Here's my midpoints. Here's my first midpoint. We'll call that one, if you want, XM1. That's XM2. Like a satellite wave. XM3. This will be XMN. Whatever. Midpoint at the different ones. So how do I get to those midpoints? How do I get these midpoints? While using delta X distances.
Was it
and
delta X over
starting
2?
point A.
It's A plus delta X over
Is that right, Will?
Is it delta X over 2?
No, it's A plus.
Oh, kind of. It's related to that. So the first one, I'm going to go over half of delta X. You're right.
Mm-hmm.
But then from here to the next one is how far?
It's a full delta X.
Full delta X. And that's a full delta X and full delta X. So another way to think of it, if we go with the half delta X that Raisley suggested, this one is 1/2 delta X over. This one is 3/2 delta X over. We follow that? 1/2, 2/2, 3/2, 4/2, 5/2.
Well, that's still over 2, so I think my point's
With always the odd halves. 1/2, 3/2, 5/2. Do you see this?
Straight jumping by odd halves. Daggone.
So how do I make odd numbers?
Was it K?
Okay, we all said it's got to be delta X over 2. I'm agreeing with that. That was a good start, but it's not all of the half delta X's. It's only the odd half delta X's. So I've got to have an odd multiplier in there somehow to get 1/2, 3/2, 5/2. So I need to generate 1, 3, 5, etc. How do I do that? Someone started saying.
Is it 2k minus 1?
Absolutely, yes. 2k minus 1 will generate the odd half delta X's.
You were about to explode.
Yeah, you're about to go like Whole Foods.
Just to make it kind of similar to the other ones, this is perfectly good, but I'm just, being a programmer, I'm going to write it so that when my notation will look the same, I'm going to have a delta X without the 2 underneath it there, and I'm going to put the 2k minus 1 over 2 like that. Anyway, it's equivalent. I just try to make it look kind of like the other one. I've got some multiplier times delta X. Over there I had K times delta X. Now I got 2K minus 1 over 2 times delta X. So this is saying to me, 1/2 of delta X, 3/2 of delta X, 5/2 of delta X. That's how I'm reading that. Either way, they're the same. That doesn't matter. It's just kind of a little pet peeve thing. Okay, so that's midpoint. One last one, I guess, and then we need to do a couple examples. How much time? Time to do a couple examples.
You got like 10 minutes.
I can get this in and then do one example.
Yeah, 7 minutes.
Okay, the last one is a unusual one. So all of the ones we've done before, up to now, the 3 special cases, even including the left side and the right side, all 5 of those special cases have formed rectangles. We went to the left endpoint and made a horizontal path. We went to the right endpoint and formed a horizontal path. We went to the midpoint and formed a horizontal path. All of those formed rectangles. It turns out to be a slightly better way of doing things sometimes. Instead of forming a rectangle, what if I form
A trapezoid.
trapezoid?
No.
Oh
No. No.
no.
That looks like it fits pretty darn good to me, just drawing in a trapezoid. So maybe we ought to study that one real quick.
It sounds complicated though.
Sounds really uncomplicated, doesn't it? So
Yeah.
now we're going to do a special case called trapezoid. So trapezoid, we'll call it T of N. It's Riemann sum, and it's going to be a little different. I'm not going to be able to specify my x sub k like this. So let me hold off on calling it too precisely. It is sort of a Riemann sum if you use the mean value theorem, but we're not going to get into that. Let me just write up what it is. So first of all, we need to understand how to calculate the area of a trapezoid. Let's do that real quick.
Oh gosh. No. What was it? That base 1, base 2 thing? Oh, curses.
So let's say this is x sub k minus 1, and this is x sub k. So this is f of x sub k minus 1, and that's f of x sub k. How do we calculate the area of a trapezoid in general? I think we went over this one time before, but let's go over it again. One way to see this is, what if I went to that midpoint right there and made a rectangle? Okay, so the idea is that this area of this rectangle is height times width. Well, it turns out that this height is simply the average of these two heights. So it's simply f of x sub k minus 1 plus f of x sub k divided by 2 times the perpendicular distance between these two parallel sides, which happens to be delta x. And then we'll just sum that up.
That's good, Brittany.
So, trapezoid formula, remember this trapezoid formula, area equals base 1 plus base 2 divided by 2 times height. That's how you normally learn area of a trapezoid. Average of the bases times the height. That's all I did right there. Let's write that out a little bit real quickly. So I've got f of x0 plus f of x1 divided by 2 times delta x plus f of x1 plus f of x2 times divided by 2 times delta x, and so on out to the last one. I don't need parentheses there yet. I'm a factor now. So f of x sub n minus 1 plus f of x sub n divided by 2 times delta x. Okay, now I'm going to factor out, folks. I'm going to factor out not just the delta x like I've done before, but because each of these has a division by 2 in it, I'm going to actually factor out delta x over 2. So I'm going to have f of x0 plus, I'm going to write out here, I'm going to have delta x over 2. But now watch what happens, folks. Yeah, I'm trying to save time because I'm running short. I've got an f of x0, but then I've got an f of x1 here, and then I've got an f of x1 there. So I actually have 2 f of x1.
Oh, nuts.
And I'll have 2 f of x2s.
Just gonna
And the last one that I'll have 2 of will be f of x sub n minus 1, and then you'll have 1 of f of x sub n. That's just an observation out greatly. Let's go back to the graph and make sure that's clear why that's happened here, everyone. On the first trapezoid, you use this left endpoint and that right endpoint to calculate the heights. And then when you do the second trapezoid, you're using that same endpoint as the left, and then that one as the right. So this one got used twice. And then over here, you're using that one twice, and so on. So you use the very first one and the very last one once, and then all the others you use twice. We clear on that? Graphically? That's where the 2's come from. Now, I don't think there's any simple way to honestly to write a new, for this one, because it's trapezoidal, there's not a nice, easy way to give the final gambit look to it. So I'm just going to stop there and see if I have time to maybe do one quick example. That's as far as I'm going to go with the trapezoid. There's not an easy way to write it in final gambit look. So let's see if we can do an example. Pick up something real quick. How about
I'm sorry. Just for now.
Bill, how about 4 minus x squared on the interval from 0 to 2 find L4. I don't know if the book uses an L4 notation. What that means is left sum with 4 rectangles. Are we clear with that? Left sum with 4 rectangles. So how would I do this? Let's see. I guess I could draw a picture if I wanted to make sure I understand what I'm looking at. So I got something like this. There's 2. There's 0. I want to make 4 rectangles in there. I want to use the left end to make the rectangles.
Oh, so 4 rectangles, is that what the...
Yeah.
So there's my picture so far.
I love it.
Oh, 0 to 2, and then I made 4 rectangles. So what's delta x equal to? Let's calculate that. Delta x. Delta x. We're back on the first board that we haven't erased yet. Minus 0 over 4, which is 1/2. That tells me my x locations. So x0 is 0, x1 is 1/2, x2 is 1, x3 is 3/2, x4 is 2.
Crap.
You clear on that?
Sure. Oh, because...
I just simply need to find the left sum area. That means I'm doing the summation A equals 1 to 4 of f of the left endpoint. Which one's the left endpoint?
0.
X of k minus 1, isn't it? So x of k minus 1 times delta x, which is equal to, so when I do, that's just the first gambit of the left sum. So now I'm going to plug in k equals 1. That means I've got to find f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. This all looks very familiar. I've done that before. Okay. Let's factor out the delta x, and we'll call it 1/2. Delta x is 1/2. That's what it says right there. Then I got to find f of x0. So f of x0 is f of 0. And then I have to find f of x1. Well, that's f of 1/2. And then I have to find f of x2, which is 1. So f of 1. Then I have to find f of x3, which is 3/2. F of 3/2. Now it's just calculating. So plug in a 0, you get 4. Plug in a 1/2, you get 4 minus a fourth. 3 3/4 is 12 15/4. Plug in a 1, you get a 3. Plug in a 3/2, you get 4 minus 9/4. So 16 minus 9 is 7/4. Times 1/2. 22/4 is 11/2 plus 13/2 is 25/2, and 1/2 of that is 25/4.
Wonderful.
Okay, I think that's it. So you have some homework in section 4.2. Using these various Riemann sums, special cases. Most of them will be that simple. We'll add in, doing n being bigger than, say, 4, very quickly we get to n is 1,000 or something. And when we get to n is 1,000, that's when we got to fall back to our sigma notation that we've done before. So now, if it's a small number, you can just manually go through like I just did. It's not that difficult. All right, see you tomorrow. And we'll eventually do n goes to infinity, which will give us the exact area instead of an approximation.
You know what? That makes sense.
Well, like when we started, area under the rate of change curve, like if you're
Carson, we have to play
got a
Overwatch.
velocity curve, and the area under the velocity curve is the
Man, I really love this Winston guy. I
Now,
like him.
there are other applications beyond simply changing position. It all comes down to, if you know the rate of change, then the area under the rate of change curve is change whatever.
Why would
Whether
you
it's
charge it?
position or
How much?
outgrowth or
Every time you're just like talking the one-liners, like every single second of it. Like, whoa.
But right now, you're right, we're just doing it as an area under this abstract function curve. I don't know what that function curve even means. It's just a function there.
But you're looking at a career in construction,
Under
so you're looking at the area under a dome.
Yeah.
If you're building the Houston Astrodome,
You need to know exactly.
load bearing, everything's
Right.
exactly.
Look at that means. Now you
And I would think, what would we do? I missed that.
I can't wait to graduate.
What did she say, where she said, turn in instead of doing?
Like if you three could just leave early since Josh is riding with you. I mean, since
Who's going?
Oh, cool.
Dylan is riding with you, that's what he said in the
Give me
Google Doc.
Judith.
Okay. He said he was gonna drive, but I can take him.
Oh, is he gonna drive?
I
Yeah.
think they're just gonna
he didn't mean that. You can go talk to him, he said driver stuff.
Oh, okay. So, yeah, if you guys need to send it early.
Oh, yeah.
Unless it's like in the middle of the test.
No,
That would
I'm
probably
gonna
not.
definitely do the test, but I just wasn't sure.
I mean, it's gonna be some pretty tough competition.
Yeah.
So it's not a thing for the awards, because I'm not gonna win anything anyway.
We get to see who wins and then see what kind of victories they do. It's always really funny, honestly.
I don't know, never. Yeah.
One of these days we're gonna all play our class as the Last Supper. The classic picture.
Oh,
Dale's gonna be in the middle.
Whoa, that's all I got to say. You have to paint it.